Hello, welcome to Boilerexams. This is the Physics 172 Exam 1 practice for spring 2023. Alright, so problem 1. A vehicle travels along a circular path as shown in the figure. From A to B, the vehicle maintains a constant speed of 4 meters per second, from B to C 8 meters per second, and from C to D 12 meters per second. What is the average speed of the vehicle in traveling from A to D? So, we know how to calculate speed in general. Speed or velocity is just some distance over some time. In the context of this problem, we know the vehicle is traveling along a circular path from A to D, so that would look like this. So we need to calculate the whole distance of this, the 3/4 of the circle, and then calculate how long it takes for the vehicle to travel along the entire distance. And then with those two numbers, we can calculate our average speed. So, in just this 1/4 of the circle, we know how fast the car is going, so we can calculate the time that it is inside that 1/4 of the circle using the distance of the quarter of the circle and the speed. So, let's do that. The time would be the distance that the car travels from A to B over the speed of the car. And so here we have meters over meters per second, and if you do the dimensions, the meters cancel out, we just get seconds, so it's all dimensionally homogeneous. That's good. To find this distance, it's just 1/4 of the circumference of the circle, so that's 1/4 times 2 pi r. And then we're given the speed, 4 meters per second. So this gives us 1/8 pi r. If we do the same thing from B to C, the distance is just another 1/4 of the circle, so the distance is the same. That's 1/2 pi over r, or 1/2 pi r. Speed is 8 meters per second, so we get 1/16 pi r. And then also another note, these are both in units of seconds. This r here, the meters in it has been canceled out by the meters in the speed, so there are no problems with the units. That's just the r is there for the number of 50 meters. From C to D, the car travels for 1/24 pi r seconds. So, with these three numbers, that gives us the t. Now we just need to know the total displacement. That's just 3/4 of the circle, so 3/4 times 2 pi r. So, the average speed is going to equal the change in x over the change in time, which is going to equal 3/2. No, hold on a second. 3/4 2 pi r times the total time, which is AB plus BC plus CD, or 1/8 pi r plus 1/16 pi r plus 1/24 pi r. And so, on the top we have pi r. Every term on the bottom has pi r, so this all cancels out. So then, average velocity, on top we have 6/4. On the bottom we have, let's see, it'd be like 3/24 plus 1/2 24. This is gross, I know. So on the bottom we get 5.5. So then if we reduce this down, we can write this as 6 over 4 over 5.5 over what would it be? 6 times 4. There we go. And then these 4's cancel. Bring the 6 up here. 36 over 5.5, which equals, I think it's supposed to equal around 6.5. Yeah. The average velocity is 6.545 meters per second. So that's our answer. Alright. So, next question. Question 2. A small space probe of mass 1,000 kilograms is launched from a space station in deep space. The space station exerts negligible gravitational force on the space probe. At time t equals 0, when the initial position of the space probe relative to the space station is 100, 200, 0, and its velocity relative to the space station is 200, 300, the space probe turns on its thrusters that exert a constant force of 4,000 minus 5,000 newtons. Using a time step of 1 second, determine the velocity of the space probe relative to the space station after 2 time steps at t equals 2 seconds. So, there's a lot to unpack here. We have some probe in space. We know its position at 100, 200, 0. And its velocity is 200, 300. So, somewhere in this direction. And then, its thrusters turn on and exert this force somewhere in like this direction. So looking at this problem, it wants us to find the final velocity of the space probe after 2 seconds. And it says to use 2 time steps, which kind of implies that the best way to do this question is to first calculate the velocity after 1 second, and then use that to calculate the velocity after another second, and that'll be your final answer. But there's actually a way to do this that is a lot faster using the momentum principle. So, if you remember, force is equal to the change in momentum over change in time, or force times change in time is equal to the change in momentum. And so generally, this is only true when we're using like dt and dp, with like very small changes in time, like stuff you see with integrals and derivatives. But because the force is constant, we can actually directly use the total change in time to get the total change in momentum of the probe over 2 seconds. And so, we'll write constant. Using this, we can really easily calculate what the change in momentum of the probe is. And then since we're given the mass and the velocity of the probe initially, we can calculate the final momentum of the probe and then calculate the final velocity of the probe. So, let's do that. Let's start with the initial momentum. That is going to be equal to the mass times the initial velocity, or actually we'll just leave it like that. It's the mass times 200, 300, 0. The change in momentum is equal to the force times the change in time. The force is 4,000, 5,000, minus 5,000, 0 times 2 seconds. Or it is 8,000 minus 10,000, 0 Newton seconds. So our final momentum is going to be equal to the initial plus the change, which is, okay, yeah, we're actually going to have to multiply our mass into here. I thought we could get away without it, but no, we have to do that. Mass is 1,000 kilograms, so the initial momentum is 20,000, 30,000, 0. Should not have put these commas in here. And that is in momentum units, which are, I'm having trouble remembering this. I don't know. We're just going to say kilogram meter seconds. And so then we just add our change of momentum, 8,000 minus 10,000. And so this then gives us 28,000. That's not putting commas. 28,000, 20,000 as our momentum. Then to find our velocity, we just have to divide it all by the mass again. And so we just divide everything by 1,000. Did I drop a 0 somewhere? Oh, I think I did. The initial momentum should have had another 0. So this will actually give us 208 and then 290. Yes. So the final velocity is 208, 290, 0 meters per second. So answer is B. So, problem 3. Using a time step of 1 second, determine the position of the space probe after 2 time steps at t equals 2 seconds. So this is actually similar to the last question, just instead of asking for velocity, it wants position. And so, to do this, it'll be somewhat similar. We can avoid doing multiple steps again because the force is constant. Since the force is constant, the velocity is linear, which means if we use the average velocity of the entire 2-second window we're looking at, we can use that to find the final position of our probe. So, what am I doing? Right, so the initial position of the probe is 100, 200. And then we want to know what it is at time 2. And then to calculate that, that's just going to be the initial position plus whatever the change in position is. And then we know how to calculate change in position. It's just velocity times some change in time. If we use the average velocity along the entire 2-second window, then we can do this all in one step and we don't have to worry about doing multiple iterations. So that would look like and then this is where the constant force comes in. Because the force is constant, the velocity is linear, and because the velocity is linear, that means if we take the average velocity by just averaging the velocity from the t equals 0 and t equals 2. That'll be the actual average velocity along the entire window. So our average velocity is going to be our initial velocity plus our final velocity over 2. We are given our initial velocity here, and then our final velocities from the previous problem. So that's going to look like, was it 200, 300? Plus 208, 290. For 2. Or the average velocity is 204, 295. Alright, so now we just calculate position at 2 seconds. That's going to be 100, 200, 0, plus 204, 295, 0, all times 2 seconds. Or we get 508, 790, I believe. Yeah. Alright, cool. Next question. Problem 4. A hockey puck slides on ice, looking down on the ice from above. Friction and air resistance are negligible. When the puck reaches location 2, it is struck hard by a hockey stick. The contact lasts a very short time. It then travels from 2 to 3 at nearly constant momentum. The magnitude of the puck's momentum is the same at locations 1 and 3. Which arrow best indicates the direction of the force applied to the puck by the hockey stick, assuming the force is constant during the contact? So, let's start with this problem. We're given a diagram which shows the momentum of the hockey puck before and after the collision. So, momentum's equal to mass times velocity. So, the momentum's in the same direction as velocity. So, this also shows the final velocity and the initial velocity. If you remember, we also have force equals mass times acceleration, and acceleration is the change in velocity. So if we find the direction of the change in velocity, we can find the direction of the force. You can kind of see it already. Our velocity is kind of rotating around. It's going from pointing left to pointing up. So you might be able to intuitively think, it seems like direction A makes the most sense to get that velocity turned around. If you look at it more mathematically, you might imagine we have our two vectors. This is VI. This is V final. If you were to subtract them and get the change, that just looks like finding the vector that points from one tip to the other. So this vector that goes from the bottom left to the top right would be our change in velocity vector, which evidently points in the same direction as A. And so that means our answer is A. Problem 5. In a crash test, a car with a mass of 1,500 kilograms is initially moving at a speed of 18 meters per second just before it collides with a barrier. The final speed of the car after the collision is 0. The original length of the car is 4.48 meters, but after the collision, the smashed car is only 3.86 meters long. Making the very rough approximation that the large force that the barrier exerts on the car is approximately constant during the contact, determine the approximate magnitude of this force. So first of all, what's this question even asking? We have this vehicle, which is crashing into the barrier on the left. And so as it crashes, the barrier is exerting some force on the car in order to slow it down until we get to the situation on the bottom where the wall has completely decelerated the car and it is now not moving anymore. And we want to calculate what the force that the wall is exerting is. So, how do we do that? We know that based on the momentum principle, force is equal to derivative of momentum with respect to time. If we assume that the force that the wall is exerting, I'm just going to call it force wall. If we assume that this force is constant, which it tells us to do, then we can further say that the force is equal to the just complete change in momentum over change in time. So if we calculate the change in momentum of the car and then calculate how long the collision is, we can calculate the average or the force that the wall is providing on the car. We are given the initial speed and the final speed, and we know what the mass of the car is, so we can calculate the change of momentum. All we have to do then is just calculate the change in time, how long the collision takes. To do that, we are given how much the car moves during a collision. It goes from 4.48 meters long to 3.86 meters long, so it travels about that change in distance. If we assume that the force is constant, then its speed over the entire collision is going to look like a straight line that's going from the initial velocity to 0. So if we have like this graph, for example, showing velocity and time, this is going to be how the speed of the car acts over the entire course of the collision. And right here where it equals 0, that's our the length of the collision. And then from here, this is the speed of the car as the collision goes on. To calculate the actual change in time, what we are going to do is approximate the velocity of the car as the average of the initial velocity and the final velocity. Since the force we're assuming is constant, it's actually not an approximation at all. It is the average speed. But since Alright, so we have change in time that's going to be equal to the displacement of the car, how much it crumples in the front, based off those two numbers. And then it is going to be divided by the average speed of the car. That's where we're going to get our change in time. Calculate our average speed. We're just going to average the initial and final velocities. The final velocity is 0. The initial velocity is 18. So the average velocity is 9. We plug that in for our excuse me. Plug that in for our equation for the change in time. That gives us 4.48 minus 3.86 over 9. Or, what would it be? Around 0.0688 seconds. I don't know if you get a calculator. I'm assuming you get a calculator during the exam. This would be not fun to do by hand. Alright, so now that we have our change in time, let's calculate change in momentum. That is the final momentum minus the initial momentum. Final momentum is 0 because the car is not moving after the collision. The initial momentum is mass times the initial velocity, so 1500 times 18. And this equals 2700. And then that's everything we need to calculate the average force. When we do the calculation, I get 3.9 times 10 to the 6th newtons. So, or 10 to the 5th. Am I reading this wrong? Oh, you know, I definitely just read it wrong. Sorry, that's 3.9 times 10 to the 5th newtons. So our answer is D. Alright, problem 6. The figure below shows two negatively charged objects with the same charge and one positively charged object. What is the direction of the net electric force in the positively charged object? So, if we look at our diagram, we have two negative charges and one positive charge in between them. We know positive charges and negative charges attract each other, so if we look at our proton, I'm assuming it's a proton, I guess it doesn't have to be a proton. If we look at our positively charged object, it is going to have a force to the left, attracting it to this negatively charged object, and a force on the right, attracting it to this object. And so, from there you might think that the total force would be 0. The two forces cancel out. But one thing to remember is that the electric force drops off with distance. So, the positively charged object is closer to the object on the left than the object on the right. So this force is going to be larger than this force. What this means is that the net force is going to be going in the left direction, or the answer is A. Problem 7. You kicked a ball of mass 2 kilograms that was initially at rest with a force 12.0 minus 16 newtons, so that the ball is now rolling on the grass field. What is the initial velocity of the ball after the kick if the duration of the kick is 0.1 seconds? So, to do this problem, we're just going to use a momentum update. Because this time is so small, we can just assume that the force is approximately constant during that interval. So, if we do that, we know that generally force equals change of momentum over change of time. If we assume that the force is constant, then we can say that the force is equal to the just absolute change of momentum over change of time. Or the change of momentum is equal to the force times the change in time. And this is only if the force is constant, or we're assuming it's constant. Since the time is so small, we can assume that during that small window the force is constant. So, let's do that. The final momentum of the ball is going to be equal to the initial momentum plus the change of momentum. The initial momentum is 0 because it's at rest, so that just gives us the change of momentum. So we get the final momentum is equal to the force times the change in time, or the momentum is 12.0 minus 16 newtons times 0.1 seconds. Once we have the momentum, we can just divide everything by the ball's mass in order to get the speed. So the mass is 2. Final velocity is equal to the momentum over mass, which is going to be the momentum all divided by 2, or 0.60 minus 0.8 meters per second. So our answer is E. Next question. The net force on the rolling ball acts in the direction opposite to its momentum. Which vector below is the direction of the net force acting on the rolling ball immediately after it is kicked? So, the net force on the rolling ball acts in the direction opposite to its momentum. So, we are told that the net force is opposite to the momentum, and we want to find the direction of the net force immediately after it is kicked. So, we can borrow our momentum from the previous question, 0.60 minus 0.8, and then if we take the opposite of this vector, which is just multiply it all by minus 1, that'll give us the direction of the net force. So, the net force is equal to minus 0.6, 0.8. So the answer is D. One thing about this is I think this question also wants you to convert it to a unit vector, but if you try to convert this to a unit vector, you'll see it already is a unit vector. 0.6 squared is 0.36, 0.8 squared is 0.64. If you add both of those and then take the square root, you get square root of 1, which is just 1. So it's not actually necessary for this question, but in general be aware that it's asking for just a direction, not an actual value. You might have to convert it to a unit vector in order to get the answer that you're looking for. Problem 9. A ball of mass m hangs by two strings from the ceiling as shown in the figure. The acceleration due to gravity has magnitude g and acts vertically downward in the picture shown. What is the magnitude of the force of tension F of t in each of the upper strings? So, if we look at our diagram, we are told, at least we are told that the ball hangs. And so, I think it's a safe assumption to make that the ball is not moving around. So, there's no net acceleration and therefore no net force. And that's going to be the key to solving this, that the net force is equal to 0. If we look at this point right here, and we draw out all the forces, we have force of gravity due to this mass m. We'll call that the weight force. And then we have the two tension forces from each of the ropes. One in this direction, and one in this direction. And so, because the net force is 0, each of these forces, when we add them all up, needs to equal 0. So, just go write that out. And then all this equals 0. And so, what we actually want to calculate is the tension force. We can calculate the weight force, that's just gravity times mass, and that will let us calculate what the tension force is. One thing to note, the force of weight is only acting in the y direction. So we can rewrite this entire equation, but just looking in the y direction. And that way we don't have to worry about messing with vectors and all that stuff. If we do that, then we get 2 times the force of tension in the y direction, and then plus the force of weight in the y direction. Force of weight, like I said, is mass times gravity. Do be careful with your negatives and positives. I'm assuming y is up. The force of gravity is pointing down, so it's going to be negative. And it's all equals 0. So now we have to calculate the force of tension in the y direction. In order to do that, if we look back at our picture, it's not a straight line. It's going to be based off of projecting this force onto the y-axis and then finding this length. So, if we look at our right triangles, we have the force of tension down here, force of tension in the y direction, and then theta. So, we can conclude that sine of theta is equal to tension in the y direction over force of tension, or that sine times force of tension equals force of tension in the y direction. So going back to our equation, we get 2 times force of tension times the cosine of theta. When we move mg to the other side, and then we just have to solve for force of tension, which gives us force of tension is equal to mass times gravity over 2 cosine theta. It looks like there's a typo in the exam. They've doubled sine and cosine. The answer is C. Or, I'm sorry. It's cosine. It's D. One thing to note is that we did this all in magnitudes and not vectors. If it wanted a vector, then we couldn't make, well, we could make it, but it'd be more annoying to like try to do this all in y's and all in x's. We should have solved it like this if we wanted the vector. Since we're only worried about the magnitude, we don't have to worry about that. And we can do it in the simplified form below. All magnitudes. Alright, next question. An elevator is accelerating downward with magnitude of acceleration a. A block of mass m hangs by a low mass rope from the ceiling of the elevator as shown. The acceleration due to gravity has magnitude g and acts vertically downward in the picture shown. What is the force of tension in the rope? So, let's see. The entire elevator is accelerating down, and then on this mass, we're going to have some force of tension and some force of weight. I'll do it in red actually. And those are only two forces acting on our block of mass. There's the force of tension and the force of weight. So we know the entire elevator is accelerating down, and if the mass is keeping tension on the rope, then the mass is also accelerating down with that same acceleration a. So we could write the acceleration of our mass m is equal to this acceleration right here, a. If we multiply both sides by m, then we get mass times the acceleration of our block of mass, which is force. Mass times acceleration is force. So this is the net force on our block, and then times mass times the acceleration of the elevator. From here, we know what the net force is. We have the two forces that make up the net force, force of tension and the force of weight. So, force of tension plus force of weight must equal mass times acceleration of the elevator. And then from here we can solve for the force of tension. So we get force of tension is equal to mass times acceleration minus force of weight. If we write it out all in vectors, we get mass times just downward acceleration. Alright. Here, we have minus a because we're accelerating downward. I'm assuming up is positive, and it is only downward, not left or right or anything, so we only have a value in the middle. And then minus the force of weight, which is 0, negative mg0. Hold on, I'm mixing units. Let's use the lowercase m. And that's the mass of the block times gravity. And it's negative again because force of weight points downwards. So if we distribute this negative in, get the force of tension is equal to, I'll distribute this in, 0, negative ma, 0, plus 0, mg0. And then we get force of tension is just mg minus ma. So our answer is D. So, question 11. Suppose that the period of a particular ideal mass spring system is 4 seconds. What would be the period of the system if the mass were 4 times the original mass? So, in this question, the period, we are told, is 4 seconds. And we know that period is equal to inverse frequency. Frequency is equal to, what is it? 1 over 2 pi square root k over m, where k is the spring constant and m is the mass on the spring. And so we are asked what happens to the period if the mass were 4 times as large. If we calculate that, we get k over 4m. We can bring the 1/4 out. We get, call this P1, call this P2. And then we get 1 over 2 pi, 1/2 k over m, or overall, P2 is 1/2 1 over 2 pi k over m, or 1/2 P1. So, if we plug in our 4 seconds, P2 is equal to wait, I realize I made a mistake. It is not k over m, it is m over k. That is my bad. M over k. So then we get 4m over k. We can bring out the 4, and we get 2 times m over k. So then we get our 1 over 2 pi square root of m over k, which is the same thing as P1, which means we can write this as 2 times P1, or the period, if the mass were 4 times as large, is double the period of the original period. So if we plug in our 4 seconds, we get 8 seconds, which is our answer. Alright. Next question. A car traverses the course as shown, which consists of 2 semicircular paths, A to B and B to C, as shown in the figure below. The speed of the car increases as it traverses the course, such that at point 1 shown, its speed is v, and at point 2, its speed is 2v respectively. How does the transverse component of the net force of the car compare at the 2 points? So, first of all, transverse component, that is the component of the net force going towards the center of the semicircle. This is our transverse component. And then we want to know, we'll call this AB, we want to know how transverse component AB compares to the component at BC. So, how do we calculate this? The important thing to remember for this question, there's one formula in particular, is that when we have some sort of object like this moving around a point in a circular fashion, this force moving towards the center, this centripetal force, is equal to, I believe, m over v squared. I believe, I'm not, believe, mv squared over r. And so this is a formula that we're going to use in order to compare the two transverse components at these 2 points in time. So if we look at our answers, it only cares about the magnitude, so I'll just worry about magnitudes too. At AB, mass is m, not changing. Speed is v, and the distance is 2r. Along B to C, the mass is unchanging, our speed has doubled, and the radius is halved. So if we expand this out, this gives us 4 mv squared over r. And so we can see from A to B on that arc, we have 1/2 mv squared over r, and then that changes to 4 mv squared over r. So it is 8 times at point 2. Alright, problem 13. A piece of cork of mass 0.01 kilograms is held in place underwater by a string. What is the tension in the string? Alright, so first of all, this cork is not moving, so the net force is 0. If we know the net force is 0, it's then a good idea to look at all the different forces and then try to see if we can calculate that force that we're actually looking for, the tension force. So on our cork, we obviously have force of tension that is pointing downwards. I'm not going to use blue for this. Let's use red. We have force of tension. We also have force of gravity, the weight force. And then, pointing in the opposite direction, we have buoyancy force. So, when we add it all in, net force is equal to buoyancy force plus the weight force plus tension force, and all that equals 0. So, we get tension force is equal to, come on, the negative weight force minus the buoyancy force. So in order, we know how to calculate the weight force first of all. That's easy, that's mass times gravity. In order to calculate the buoyancy force, we are going to use buoyancy force is equal to the displaced volume times the density of the water. Rho is used for density, I believe. Density of the water, and then all times gravity. So we are given the density of the water. We just need to find the volume of the cork, which is the volume that is being displaced here. So we aren't given volume. We are given density and mass though, so we can use both of those in order to find volume. So if we have 0.01 kilograms, and then the cork is 250 kilograms per cubic meter, and that means our volume is 0.01 over 250 meters cubed. So, returning back to our overall equation, F of T is going to be equal to the weight force. I'm going to say up is positive, down is negative. So we're going to have another negative, and then buoyancy force, water is 1,000 kilograms, all times G. Or we get come on. We get that much G minus this much G. Alright, 10? Yeah. Alright, and then we just have to calculate what the force tension is. Wait, hold on. Oh yeah. And one thing to note is that this is going to give us a negative number because force tension is pointing down and we define down as negative. So for a second I was like, we're getting a negative number, something's gone wrong. That is normal. So we get the force of tension is negative 0.3 newtons. So our answer is C. Alright. Next question, question 14. A thin platinum bar is 1 meter long with a 1 millimeter by 1 millimeter cross section and is attached to the ceiling. When a 10 kilogram mass hangs from the bar, it stretches 2 millimeters. If we hang the same 10 kilogram mass from a 2 meter long platinum bar that has a 2 millimeter by 2 millimeter cross section, how much will that bar stretch? So this is a question about the Young's modulus, Y, of a material. And so that tells us that for a material, the strain, the force over the cross-sectional area, divided by the percentage change in length is constant for one material. I'm just going to put change in L over L. So this in total says force over area times the change in length over length is constant for one kind of material. So in our question, we have two different platinum bars with different cross sections and different lengths with the same force being applied. In order to determine how much the second bar will stretch, we use the first bar to determine Y of the platinum, and then from there we can calculate the amount that the second bar will stretch. So let's do that. Y for the platinum. What's platinum's symbol in the periodic table? PL. Platinum's Young's modulus is going to be equal to the force. The force is 10 kilograms in gravity. So that's going to be m times g, where the m is 10 kilograms. This is all just magnitudes. We don't have to worry about vectors. So no negative, just mg. The cross-sectional area is 1 millimeter times 1 millimeter. That's going to be 1 millimeter squared, or a thousandth of a meter squared. And this is all over the change in length, which was 2 millimeters, or 2,000ths of a meter, divided by 2 meters. We're just going to use 10 meters per second squared. Running out of space. Alright, plug this all in, we get a large number. Y, the platinum, is 10 to the 11th. What are the units, like pascals? Let's not worry about the units for now. So with this number, we can then take the same equation and then plug in our numbers for the second bar. So the second bar has the same mass, 10 kilograms, times gravity. Cross-sectional area is 2 millimeters by 2 millimeters. That's 2 thousandths of a meter squared. And then we want to know change in length. The length is... Hold on a second, I made a mistake. I used the wrong numbers for the first bar. It's only 1 meter long. Wait, I did it again. There we go. And that will cause our answer to be 2 times as big. And then our second bar is 2 meters long. So, all of this is with a platinum bar, so we can use our Young's modulus that we just calculated. And then from here we just have to solve for the change in length. So, let's do that. If we divide by the force, multiply by the area, we get 2 times 10 to the 11th, 0.002 meters squared. All this over 10 kilograms, 10 meters per second squared. And then divide by 2 meters. No, multiply by 2 meters. And on the right, we're going to have 1 over change in length. So then we can just flip everything around, and we get change in length is equal to 10 kilograms, 10 meters per second squared, all over the y. Alright, and then this equals getting the wrong answer. Alright, I found the mistakes. There were 2 actually. First of all, when I replaced that 2 with a 1, I did not recalculate the Young's modulus right. It comes 5 times 10 to the 10. Come on. Now I can't even write. Oh, there we go. Come on. Alright. So, Young's modulus was 5 times 10 to the 10th actually. And then here, that 2 meters is on the wrong side of the denominator. And then we fix both of those mistakes. That gives you the correct answer, 1 millimeter. And so that is our actual answer, B. Alright, problem 15. Two boxes move together with the same acceleration across an icy surface as you push with a horizontal force of magnitude F as shown below. The mass of the box 1 is 60 kilograms and the mass of box 2 is 20 kilograms. What is the best estimate for the magnitude of the net force acting on box 1? Alright, so looking at this question, what is happening is we have these two boxes, and they're both being accelerated by this force F. And so you can think of it as like both of these boxes are using like some amount of F. Box 1 is using, a little bit of F, and box 2 is using a little bit of F. And both of the amounts they use are to accelerate them. Because both of these boxes are moving together, we're actually told this explicitly. They both have the same acceleration. So we can calculate what the acceleration of one box is as in terms of this F here. And we can also calculate it in terms of the individual forces acting on a single box. And so that is the idea we're going to use in order to calculate what magnitude of the net force is acting on just one of the boxes. So let's go ahead and do that. We want to find the magnitude of the net force acting on box 1. So we want to find the amount of F acting on M1. If we look just at box 1, there's only two forces acting on it, the weight force and this proportion of F. We'll say F of M2 because it's being pushed by box 2 into box 1. So then, we know force equals mass times acceleration. If we look at only the x direction for box 1, in the x direction our only force is F of M2, and that's equal to mass times the acceleration in the x direction. So if we rearrange this, we get the acceleration of box 1 in the x direction is equal to force of M2 over M. And so if we think about what this force of M2 really means, the amount that box 2 is pushing on box 1 is the amount of force that the amount of the net force that is acting on box 1. So M2 is the quantity that we want to calculate, and whatever that is in terms of F will give us our answer. I'm realizing now we probably should have kept it in these terms. This is the thing that we want to calculate. So, in order to get in terms of F, this F right here, we next need to look at this system of boxes as a whole. So, let's do that. We're going to do this on the x direction again. So, if we have both boxes, the forces are going to look very similar. We have the weight force, which is not in the x direction, so we don't care about. And then we have, that was not straight. And then we have our force in the x direction, which is just our F. So, if we do the same equation, force equals mass times acceleration. So, our force is going to equal to our mass times acceleration. realizing now, I shouldn't put that there. And then this acceleration is also in the x direction. And then, if you remember, we are explicitly told that both boxes have the same acceleration. So this ax must equal this ax. And that's the fact that we can use to find f of m2 in terms of f. Realizing now we did need f of m2, or yeah, in terms of a of x, or the other way around. We need a of x on its own. A of x equals f m2 over m. And then we just plug it in. So, yeah, we'll stay with blue. F of m. Hold on a second. This is mass 1. This is total mass. So this is what we want to calculate. We wanted to find f of m2. So f of m1 over m total equals f m2. Look back at our question. Box 1 is 60 kilograms, box 2 is 20, so the total mass is 80. So we get f of 60 over 80. So that is 3/4 f. So our answer is C. Alright, moving on to the next question. Problems 16 through 19. A block of mass m is attached by a spring with stiffness K of S to a wall at the top of a slippery ramp as shown in the figure. The spring's relaxed length is L0. At time t equals 0, the spring's stretched length is L and the block's velocity is v of I. Which of the following is an accurate free body diagram representing the forces acting on the block? Alright, well, look at our block. We are obviously going to have the weight force. And then it is sitting on this incline, so we're also going to have a normal force. The normal force is perpendicular to the incline, so it'll be something like that. It's going to be our normal force. And then the other force that we're going to have is caused by the spring, and that is going to be in this direction. If the spring were being contracted instead of stretched, then the force would go in the opposite direction. But right now it's being extended, so it's trying to pull back up the ramp. And so those are our three forces. When we look at our answers, they want all the forces in the x and y directions, where x and y is, as on the plane. So in order to do that, we need to rewrite the weight force in terms of its x and y components. So we have to do some right angle trigonometry. I'm going to just erase this for a quick second. We're going to have the weight force in the x direction and in the y direction. And then, let's see. Then we have the actual just weight force. And this all makes a right triangle. So, I believe visually, this angle at the top, this one right here should be theta. I'm trying to think about how you would confirm that. Let me redraw this over to the side. So we have our angle theta, and then we have our FY direction. Oh, I realized I wrote this backwards. So we have something like that. Or I drew this backwards. If we imagine, let's do it like this. So we have our slope, theta, and then if we put all of our forces at this corner, then we have F of y, force of weight in the y direction, and then this is force of weight in the x, right angle. Then right here is just the force of weight. And then from here, this is hard. Alright, here we go. Now I've got it. Alright, so we got our three forces, FWY, F of W, and FW of x. And then this is a right angle. And this is a right angle. So with both of those, we can determine that these two angles must both be theta, because if we look at, let me switch colors. If we look at this right angle, it has the left angle of our three forces and this middle one. And then if we look at this right angle, it has the angle of our incline and this inside one. And since they both share the inside one, the other two angles must be the same. So there we go. That's how you prove that this interior angle right here is theta. So with that, then we can then do our calculate what the FWY and FWX are. So from here, it's just a right angle trig. We have theta, and we want to know what FWX is. This line right here is FW of x, so that's opposite over hypotenuse. So sine of theta is going to equal FW of x over FW, or FW of x is equal to sine theta FW. And then similarly, cosine theta is going to equal FW of y over FW, or FWY is equal to FW cosine theta. So, looking at our answers, this one is wrong, it has the spring force in the wrong direction. This one is wrong, it has the spring force in the wrong direction. This one, C, is correct. One thing, they've substituted in mass times gravity for the force of weight. You know, force of weight is mass times gravity. But other than that, it's the same thing as what we drew up. So C is correct. And then D is wrong because it has the cosines and the sines flipped. Sine of theta goes with FW of x. So, answer C. Alright, what is the net force acting on a block, given all those parameters up there? Well, net force is just all the forces summed up. So F net's going to equal to gravity plus spring plus normal force. So, actually, I'm going to write this with F, the force of weight in the x direction, the force of weight in the y direction. I think that'll make things easier. So then, net force is going to be equal to force of weight in the x direction. Calculated that was, let's see, sine theta FW. And then the force of weight's mass times gravity. So in the x direction, we get mass times gravity times the cosine, sine of theta. And they have x in the positive direction going to the right. The force of weight in the x direction is going to the left, so that's going to be negative. And this is all in newtons. Our other force of gravity in the y direction, is going to be very similar, both cosine theta. In hindsight, why did I... Alright, I'm not sure why I split up force of weight into x and y actually. I could have just done that all together. Spring force. Calculate the force of a spring. It is... Where do I want to write this? Let's write it over here. Force of the spring is equal to negative kx, where x is the displacement and k is the spring factor. So, let's see. We're given k of s is 15 newtons per meter. And then, I believe from the picture, we can find the displacement. That's s. And then, spring force is acting in the positive x direction. So, we will get, come on, positive 50 s. I'm not going to substitute anything in yet. We're going to do k of s. And this is positive because it's acting in the positive x direction. I know the equation I put has a negative in it. That is because the displacement is going in the negative x direction. So those two negatives gives us positive x direction. Then the last force, normal force. We can't actually do anything besides just write the normal force. We can't do anything beyond that. The normal force is dependent on all the other forces. In this case, because we know that the block of mass must stay on the ramp, we know all the forces in the y direction have to cancel out, and so the normal force would be scaled so that all the forces in the y direction cancel out. I don't think in this question we actually need to calculate that. Actually, with that being said, we know all the forces in the y direction must cancel out, and we can see all of our answers have 0, the y component. So, calculating the net force, I'm just going to ignore the y component and we're just going to focus on the x component. So, finally, we have Ks minus Ng sine theta. And here I think we can just plug in our numbers. So K was 50. The displacement is L minus L0. L is what? Minus 0.6. L0 is 0.5, so S is 0.1. Minus the mass of the block, 5 kilograms. Gravity, we'll just say 10. And sine theta, where theta is 30. Alright. And then this gives us 5 minus 50 sine 30. Sine of 30 is what? 1/2? Yeah, 1/2. So 5 times 10 times 1/2, 25 newtons. So F net in the x direction is minus 20 newtons. And then we know in the y direction it has to be 0. I'm just going to write that over here. And so then our answer is A. Yeah, the answer is A. Sorry, I got confused for a second. Alright, problem 18. What is the momentum of the block in the time interval of 0.1 seconds? Alright, so is this asking for the momentum of the block after 0.1 seconds? Yeah. Alright, so what's the momentum of the block after 0.1 seconds? So to do this, we just take the force, and we're going to assume for that 0.1 seconds the force is constant, and we just use that to calculate what the momentum would be after 0.1 seconds. So in equation form, we know force is equal to the change in momentum. If we assume force is constant, then we can write this as force is equal to the change in momentum over change in time, or force times the change in time equals change in momentum. And so this is what we're going to use in order to calculate the new momentum. So after 0.1 seconds, the final momentum is going to equal the initial momentum plus change momentum. The initial momentum is the initial velocity times the mass. Equals 5 kilograms, right? Yeah. And then the change of momentum is the force times the change in time. So the force was minus 20 newtons. And change in time is 0.1 seconds. So final momentum is minus 500 plus minus 200. So our answer is minus 700. Problem 19. What is the position of the block at the end of this time interval of 0.1 seconds? We're going to do the same thing as with the momentum. We're going to do an update. Very similarly, acceleration, sorry. No, yeah, velocity. velocity is equal to the change in position. I'll use that for position. Change in position over change in time. Since the time interval is short, we're going to assume that the velocity is constant. Since the time interval is short, we're going to assume that the average velocity over those 0.1 seconds is just the average between the start velocity and the end velocity. So we will write the average velocity is equal to the change in position over change in time. Or we can find the change in position by change in time times the average velocity. And so it looks very similar to the equation we just used for momentum. So writing this out fully, the final position is going to equal to the initial position plus the change in position. So we get initial position plus the average velocity times the change in position. Or sorry, that backwards. Times the change in time. So let's calculate the average velocity. Or to calculate the average velocity, we need the initial velocity and the final velocity. We know the initial velocity, it's given to us. To find the final velocity, we use the momentum we just calculated, minus 700. If we divide that by the mass, we get the final velocity. So V of F is going to equal P of F over M, which is going to be 7 over 2, or 1.4, minus 1.4. Meters per second. So then our average velocity is going to be, what, minus 1 plus 1.4. Over 2, or we're going to get minus 1.2 meters per second. So then, just plug this all back in. Final position is going to be equal to the initial position, minus 0.6. Sorry. Plus our change in position, which is going to be minus 1.4 times 0.1. Come on. Which is going to be just minus 0.14. So then we get minus 0.74. That is our answer. All right. Next question. Both boxes are initially at rest on horizontal ice. You apply a force as shown on the top block such that the two blocks move together. Which of the following is the correct free body diagram for the system comprising both blocks? That is important. Well, let's look at what we have. So, both blocks, we have a force acting on it, moving to the right. So that is, I'm just going to draw this over. Come on. This is our F. We have the weight force, which is going to be the mass of both blocks times gravity. We have the normal force. And then we have, that's it actually. There's no friction because it's frictionless. So these are the three forces. So looking at our answers, they all include friction except for C. C has no friction. We are explicitly told there is no friction, So that's kind of curious. The answer is evidently C. But otherwise, you can see C lines up with what we wrote down. We have our force F, the force of weight, and then it has the normal force is written down as the normal force of 1, mass 1, plus the normal force of mass 2. As you can see, C is the answer. Next question, 21. What is the magnitude of the acceleration of the system of two blocks moving together? Alright, so this is just a straightforward force equals mass times acceleration. We want to know the acceleration of both blocks. So we have force. The only I should be careful how I word this. There are three forces acting on the blocks. There's a normal force, the weight force, and the this force F. But the force of weight and the normal force cancel each other out. So the only thing we're left with in terms of net force is just this F. So let me write that out. So then we get F net is the same thing as F, which equals total mass of the system times the acceleration. And the acceleration is what we're trying to find. So then if we just rearrange it a little bit, we get A equals force over total mass, which is m1 plus m2. And it just wants magnitude, so we'll get rid of these. So that's our answer. Alright, next question, 22. Which of the following is the correct free body diagram for the system comprising only the bottom block? So, if we look at just the bottom block, there's going to be some similarities, some differences. We're still going to have weight. We're still going to have normal force. But the big difference is that this force F does not act directly on the bottom box. It only acts on the top box. So our force in the right direction is not going to be F. If you think about it, both blocks are moving together, but only the top block is the one being acted upon. So there must be some friction or something between the two blocks that are moving them together. And that is the force that is going to be moving the bottom box to the right. So I think in all the diagrams they're assuming it's friction. So that's how I'm going to write it. Friction 1 on 2. Now we go to our answers. We can reject A and D because they both include F as acting on box 2. So the answer is B. C is wrong because the friction is moving box 2 to the right, not to the left. Alright, last question. What is the magnitude of the force on the bottom block due to the top block? So it wants us to calculate this. Similarly, f of n and f of w are going to cancel out. So let me just write that out. Alright. So that's what we're trying to find. We want to find this. So how do we do that? Well, if we look at the forces on only mass 2, we know that box 2, we know that F net must equal the mass of box 2 times its acceleration. We know the net force. Come on. We know that the net force is equal to the force of 1 on 2. And then we know that the acceleration of box 2 must be equal to the total acceleration of both boxes together, because they're both moving together. And if they're moving together and they're being accelerated, they must be being accelerated together. So we get F of 1 on 2 is equal to mass 2a. If we go back to 21, we got this expression for the acceleration of both boxes together. And like I just said, box 2 and both boxes together must have the same acceleration. So we can actually take this expression right here and plug it in for A in our expression for box 2. So we get mass 2 times the force over mass 1 plus mass 2. And then this is our answer. If we just rearrange it a little bit, we get mass 2 over mass 1 plus mass 2 all times F. So C is our answer. And, oh, there's one more question, never mind. A truck driver slams on the brakes, changing the velocity of the 1,000-kilogram truck from 21 meters per second to 5 meters per second in 2 seconds due to a constant force on the road of the truck tires. What force was exerted by the road on the tires during this interval? So, I think the best way to approach this would be momentum. I don't know why it keeps on doing that. Oh, I just figured it out. Alright, anyways. So, force is equal to the change of momentum over time. If we're assuming that the force made by the road is constant, then we can just write this as force is equal to the change of momentum over the change in time. Or the force... Actually, we're going to leave it like that. So, now we have this expression. Since we're assuming that the force on the road, or the force on the truck tires by the road is constant, we can write force of the road is going to be equal to the change in momentum of the truck over the change in time. So now we just calculate these numbers. The change in momentum of the truck is going to be the change in velocity of the truck times its mass, and we're given the change in time. So, velocity of the truck changes from 21 to 5, so that'd be like minus 16. And then its mass is 1,000 kilograms. And then all this over the change in time, which is 2 seconds. So 16 times 1,000 is 16,000. Divided by 2 is minus 8,000. So the force of the road on the truck tires is minus 8,000 newtons. So the answer is D. And now that is the last question of the exam. Alright, I hope you enjoyed.